Hi, my name is Leandro da Silva, and I'm a master degree student at the State University of Santa Catarina. In this video, I am showing to you the bridgeless converter using LEM-OCC-SDS control. This control is leading edge modulation, one cycle control, simplified distortion, and stability. The topics covered in this presentation are going to be bridgeless totem pole topology, the LEM-OCC control, especially focusing on the harmonic distortion and stability. The first extension proposed, which is the improved stability, the second extension, which is the improved stability and distortion, and the simplified analog implementation, which is named SDS, which stands for simplified. Talking now about the bridgeless totem pole rectifier, or TPBR, totem pole bridgeless rectifier. It reduces conducted losses in comparison with the conventional boost rectifier, or BR, by removing a semiconductor from the current path. The common mode noise generation is similar to the boost rectifier and is slower than the conventional bridgeless converter. The bridgeless converter conventional is the one which has the two low side switches. The two main problems with this topology is the difficult to measure inductor current in an economical way without use of Hall sensor or current transformers. And they were initially limited to operating DCM due to the switch body diode reverse recovery time of the switches. However, using GaN devices nowadays, the efficiency can be higher than 99%. The first control proposed is the LEM-OCC, which is the conventional control. This is the conventional control for one cycle, and it has problems related to the stability and distortion when it's used for the bridgeless converter. So the LEM-OCC for the TPBR, it has a structure as shown in this figure, and it allows the use of a shunt resistor in the current path instead of a Hall sensor. The shunt resistor is this one, and the current path is the current IDB. The problem with this control is the instability and high total harmonic distortion when it's operating with low load and high input voltage. It is derived from the generalized PFC modulator, which was proposed first in 1998 by Smedley. So now using the LEM-OCC for the TPBR. The topology for the control is shown in this figure, this first figure. The first thing that has to be done is the working switch has to be chosen based on the input voltage polarity, which is done by this comparator and also by these two AND gates. When the voltage across the shunt resistor meets the control voltage VM, integral voltage, the reset flip-flop resets, turning the working switch and resetting the integrator, which means that whenever the voltage across this resistor is higher than the integral of the control voltage, this comparator will reset this flip-flop. When this happens, the complementary output of this flip-flop will go to high state, and it will simultaneously reset this integrator. The voltage VM always determines the output desired power, or equivalent resistance, as seen by the input source. The current value will also naturally follow the input voltage waveform. The main problems with this topology of control is the fact that even though the current waveform in the valley follows the input voltage, the mean or average current waveform will not follow the input voltage because it's given by this expression here, which has a term which has a term 1 and another term which is responsible for the distortion, which means that the input average current will be the input voltage divided by the equivalent input resistance multiplied by 1, which gives the sinusoidal term, and another term which gives the distortion term. Now, it's possible to calculate the input current waveform and decompose it using the Fourier series. Before decomposing it, we need to calculate the coefficients K1 and K2 based on the circuit parameters, and based on the expression for the Fourier series, we can determine the amplitude for each one of the harmonics. An interesting fact about this graphic is that the amplitude of each harmonic is inversely proportional to the third power of the order of the harmonics, which means that n times n squared minus 4 at the limit when n tends to infinity will be equal to n to the third power. In this way, we can calculate a closed form for the THD and also for the power factor of this converter. The stability will be given as functions of the parameters K1 and K2 as well. And in those two figures, you can see how the converter behaves using this control. The shaded area or volume, it determines the region where the control is stable. It's an area that is very restrictive, as will be shown later. And as can be seen, the THD is not very high. It's about 16%. And also the power factor is about 98. It's above 98%. The main problem with this control is that it's very restrictive in terms of stability, which means that this volume in black and in pink, they are very small when you need to use this control. Now, performing a stability analysis in this control, we can see that the peak current in one switching cycle will always depend on the previous peak current in the previous cycle, multiplied by a constant called Ks. This constant will determine the poles of this system. It cannot be higher than 1 in absolute value, as shown in this last equation. If Ks is higher than 1 or less than -1, it will be unstable in that switching cycle. Using the expression or the formula for Ks, we can calculate the conditions in which there will be instability in this control. And this expression is given by this last formula, and it's very restrictive, as can be shown in these two conditions. The one-cycle control will be always stable if the output voltage is higher than 2 times the peak voltage of input voltage whenever the equivalent input resistance is infinite or the output power is 0, or if the output power is higher than a minimum value, which means that I have to have a minimum amount of load in order to ensure that the output, that the control will be stable. If those two conditions are not met, we will have instability, as shown by this figure. The stability will always show in the peak current, which means that it will always show in the about 90 degrees of input voltage. And in order to solve these problems, three extensions will be proposed in which fictitious current is used and added together with the shunt resistor signal of the sensor. The first attempt to improve the stability of this control is called LEM-OCC-SDS, where S stands for improved stability. In this control, it's similar to the previous one. However, the current coming from the shunt sensor will be added together with the input voltage divided by a fictitious resistance, which will produce a fictitious current. So a fictitious current proportional to the input voltage is added to the current current path IDB. This fictitious current emulates a resistance RF in parallel with the input equivalent resistance, which means that the new resistance will be the parallel equivalent of RE and RF. And the modulating voltage will determine the equivalent resistance, which will finally determine the output power desired at the output of the converter. So this strategy, it allows this stable operation down to 0 watts and also discontinuous conduction mode of this converter, as can be seen in this figure. Whenever the whenever the input current touches the 0 amps current, the only current which will be controlling the duty cycle will be the fictitious current, whereas when we are working with in CCM or continuous conduction mode, the sum of the feedback current from the shunt sensor and the input current from the fictitious current, in fact, will be the which will determine the duty cycle of the converter. The semi-stability criteria used for the LEM-OCC, the conventional control, is used just replacing RE with RE key. So it's the parallel combination of RF and RE. In this way, the expression is the same. However, now we can calculate RF to be a minimum value, which will ensure the stability region down to 0 watts. So a maximum value for the fictitious resistance can be calculated, or a minimum fictitious current, which is the same thing. So a minimum fictitious current RMS can be calculated and has to be higher than this value to ensure the operation down to 0 watts. This strategy, this extension, it solves the problem of instability. However, the input average current distortion will continue to be still the same as the LEM-OCC, the conventional control. As can be shown in this last equation, the expression for the average input current will continue to be the same as the previous control. And as an example of this control, in this figure is shown the input voltages in green, the input current in red, and the average of the input current is shown in blue. The current is not, the control is not unstable. However, it has a very high total harmonic distortion, as can be seen, because the blue current do not follow a sinusoid. In order to solve this problem, it can be cancelled the terms which relates to the distortion in the equation for the average current. For this extension, the name is LEM-OCC-SD, which means distortion and stability. This control, it ensures the operation of this converter down to 0 watts, as well as the operation without any harmonic distortion. So the control is still the same. However, now the fictitious current has two terms. One of the terms ensures stability, which is given by IF superscript S, and a non-sinusoidal term for obtaining 0 THD, which is IF superscript E. The non-sinusoidal term has to be obtained for CCM and DCM independently, because the expressions are different. In DCM, the control is already stable, so the sinusoidal term is not necessary for this condition. For the case where the converter is operating in CCM, it's necessary to apply a term of a sinusoidal term for the input current, for the fictitious current, and a fictitious resistance can be calculated to be less than a maximum value given by this formula. In DCM, only fictitious current controls input current. This control is always stable, which means that the peak of one switching cycle do not depend on the previous peak of the input current of the inductor. In this condition, in DCM, the converter it operates as a voltage follower in which the input current naturally follows the input voltage. Now the term for the fictitious current, which relates to the distortion or THD. Now the term responsible for reducing the input current distortion has to be calculated independently for the cases where the converter is operating in CCM and in DCM. In CCM, the input average current can be calculated using this formula. So in order to eliminate this term, which relates to the distortion of the input current. This fictitious current has to be calculated to cancel out this factor, this term. And it's very easily calculated as shown in this expression. In DCM, it's a little bit more complicated, but it can also be calculated, and the result will have a square root of all the parameters in the circuit, and it has to be calculated recursively in order to perform this control. It means that a microcontroller or a digital signal processor has to be employed in order to calculate this expression. So it's very hard to calculate it using analog circuitry. The mode detection, which means that how to detect when the converter is operating in discontinuous conduction mode or continuous conduction mode, can be accomplished by calculating the intersection of calculated duty cycle values, or the theoretical duty cycle values. And also the control voltage can be calculated based on the output desired power, which means that given a desired power, I can always calculate modulating voltage for the controller. Here's the schematic diagram of this control. Here at left, it shows the calculation of the continuous conduction mode fictitious current. Here it shows the discontinuous conduction mode fictitious current. Here happens the mode selection for this current. And here the mode detection for this, which will determine which one of these two currents will be applied as the fictitious current. Here there is a simulation for this converter as operating in 25 watts of output power. As can be seen, the valley current do not follow a sinusoidal shape anymore, and neither do the peak current of the inductor. However, the average current will be a sinusoid because of distortion terms have been cancelled out by the fictitious current. The last strategy, or the last extension, is the SDS, where S stands for simplification or simplified, which allows the use of analog circuitry. In this control, basically, the fictitious current is chosen to be a constant value inside the grid current period. A and B are constant values and positive values. Pref is the output power, which is the desired output power. In this case, whenever I need more output power, I always can reduce the input fictitious current, because this control will tend to naturally be more stable whenever the output desired power is higher. Here is shown the figure how the two terms relating to the stability and distortion for this fictitious current, which is a constant, can be calculated. In fact, the term relates to the stability, continues to emulate equivalent resistance or fictitious resistance, whereas the sinusoidal term, it relates to the distortion. So the stability criteria now is given by this expression here. And also the modulating voltage can be calculated based on the output desired power. The two values of A and B can be calculated based on the expression for the stability, which will yield the initial values for A and B. And an optimization algorithm can be used in order to calculate which values for A and B are more appropriate for the use for this converter. In the case, the constants Ka and Kb multiply A init and B init to yield the values for A and B. And the THD is calculated, and the sum of the THD across the full range of power in which will be employed the converter is added together to yield the value of C. The implementation of this control is very simple, as can be shown as is seen in this figure. And the fictitious current is a constant which depends on Pref, which means A minus Pref B. It's limited to 0, which means that it will never be negative. And also Pref determines the modulating voltage for the control. This graph shown here, this chart, it shows for several values of Ka and Kb, how the sum of the total harmonic distortion will behave. And the optimization algorithm can be used to select the best values for Ka and Kb. In this case, the sum of all the power points here, which minimizes this controller, was found to be Ka equals to 1 and Kb equals to 0.4. And the sum of the THD was equal to 314. In these points, shown here, is where this limiter will work, limiting the fictitious current to be 0, which means that above these points, there will be no fictitious current, and the control will behave just like the conventional one-cycle control leading edge modulated control. Here is shown a simulation of the input current for the condition where the output power is 25 watts, Ka is equal to 1, Kb is equal to 0.4. As can be seen, the input current is very distorted, and the THD is equal to 61.2%. On the other hand, in the output power of 300 watts, using the same constants for the Ka and Kb constants, we can see that the THD, or the harmonic distortion, is much lower than for the case where the output power is lower. So the final remarks about these three strategies, or these three extensions, is that the first one can be used to eliminate the instability. The second one can completely eliminate harmonic distortion, at least in theoretical calculations. However, it needs a DSP or a microcontroller in order to implement the square root calculation. A simplification allows the implementation of this control using analog circuitry at the cost of a higher THD. And the THD values obtained in this presentation is in good agreement with the values found in the paper by Fisher. Here are the references for this presentation. The first one from Smedley, and the second one from Fisher. Thank you.